Okay, hello everyone. So at the end of the experiment, we will have our data in an Excel spreadsheet, as you can see. Now first, you need to convert the load data given as kilogram forces to newtons by multiplying the load column with 9.81 and the strain values are directly obtained from the video extensometer. You need to convert them to actual strain by dividing 200 since it's given as a percentage. Then you will plot the stress versus strain diagram. So as an example, select those values and drag them. There's going to be a lot of data, a lot of rows. Okay, so when you multiply it by 9.81, you will get them in terms of newtons. Now, this is load in newtons, and this axial strain must be divided by 100. So you select this, divide by 100, do the same thing again. Okay, now we have the actual strain values here. This is strain and it's unitless. Now we copy the load data and put it here. Now after that, all is done. Now you need to convert this load to stress by dividing with the initial diameter measured by the caliper. You need to calculate the area of a circle since the specimen is cylindrical. Afterwards, you will obtain the stress values. Then we will plot them as a scatter plot to find stress versus strain diagram. And since the if you watched the actual experiment video, during the elastic deformation stage, the initial values, the elastic deformation values, will have some errors due to machine stiffness. I will explain them, and the sliding of the specimen between the grips. So we have two effects that influence the elastic values. One of them is the, as I mentioned, the sliding of the specimen. So if we have the specimen during elastic deformation stage will not stay still. It will actually slide between these jaws, and due to the slipping, the elastic elongation values will be influenced. Besides that, if you look at the whole machine itself, okay, this machine is also constructed from different materials, right? So we will have the elongation of the machine itself as well. So that also influences the elastic range, elongation and stress values, load values, and we call that effect machine stiffness. Okay, Now the stress values that we calculate, if we divide it by the cross-sectional area and we take this as millimeters, then this is millimeters square. Newtons per millimeter square will give you megapascals. After that, we insert a scatter plot. We select the data. Let's name this as steel. Sorry. The x values will be our strain values, and the y values will be our stress values. There. This is the typical behavior for a plain carbon steel. This is a 1040 steel. As you can see, there are lower and upper yield points around here. One thing to mention, you must format your axes properly, and you also must label your graphs properly. You have primary horizontal, primary vertical. So this is the stress in megapascals, and this is the strain, which is unitless, but by convention we say that this is millimeter per millimeter. Now, after we obtain the stress-strain diagram, I will also show you how to apply the 0.2% offset yield method. So, since this was a plain carbon steel, it will show upper and lower yield point phenomenon here, but not all materials, in fact most metallic materials that you will work with, will not show this behavior. So first we must calculate the Young's modulus in order to apply this offset method. I have selected two random points around somewhere here and calculated a slope from there. The stress values were these, 317, 298. These were the strain values, and from that, since the value here is in megapascals, you must divide it to 1000 to get gigapascals. We get something like 228, which is pretty close to actual Young's modulus of the steel, which is around 229, 230. Generally, for steels, 200 gigapascals is the Young's modulus. So, after you find this value, you must plot the offset line. Okay, so we need to calculate or find what the offset yield strength value is. So we start by plotting this line. We start the x values from 0.002, increase them by an increment of 10 to the power minus 6. It has to be small so that our resolution to find the yield strength is high. Then we multiply the x minus 0.002 with Young's modulus and calculate y values. So here are those columns. We start from 0.002, then increase them by 10 to the power minus 6 here. Then we take the Young's modulus value in megapascals, assign them as a constant. This is how we assign a constant in Excel. Then you multiply them, and these are your y values, the stresses in megapascal. Again, you need to input a lot of values since we are increasing them by a very small amount. So we find them around, we need to input like 2200 x values, and from the offset line we read it as 410 megapascals. This is your yield strength value, and the corresponding strain value will be your strain at yielding. So since this is a plain carbon steel, you can directly report the upper and lower yield strengths, but if the material is, for example, aluminum or another type of steel, you need to use this offset method. The maximum point of the stresses is going to be your ultimate tensile strength. This is the point of fracture, so the last point that you read here, this is your fracture strength, and the corresponding strain is fracture strain. And for UTS, this strain has a special name. It is the maximum uniform strain, meaning that beyond the UTS we have non-uniform strains since necking and strain instabilities begin. And this concludes how you calculate the required parameters.